Okay, we are beginning our linear equations unit with lesson 3-1, rate of change. Okay, so here are our standards for this lesson. We're preparing for standard 8.ee.5, and that's graphing proportional relationships, interpreting unit rate as the slope, comparing two different proportional relationships represented in different ways. Okay, there's a lot going on there. We will get to each of those things in bits and pieces. Our mathematical practices are making sense of problems, persevering to solve them, construct arguments and critique the reasoning of others, model with mathematics, and select appropriate tools. Okay, our question for this lesson is, why are graphs helpful? So we're going to be using graphs to help us answer some questions and determine certain things about different functions. Okay, so to be able to do that, the things that we need to learn are to use a table and a graph to determine if there's a proportional relationship, and we'll talk about what that means, and determine what the constant rate of change of an equation is. So those are the two main things that you should learn by the end of this lesson. Okay, we're going to have two vocabulary words, so because this is a new unit, you'll want to start a new vocabulary page, and we just have two words for this lesson: linear relationships and constant rate of change. All right, finally we're getting to this worksheet. Take a look at our first problem. Is a real-world link talking about music. Marcus can download 2 songs from the internet each minute. This is shown in the table below. So if you look at our first row, we have the time that it takes to download and the number of songs. So in 0 minutes, obviously 0 songs, makes sense. After 1 minute, 2 songs have downloaded. After 2 minutes, 4 songs have downloaded. After 3 minutes, 6 songs have downloaded. So you probably notice that there's a pattern. It says, number 1 says, compare the change in the number of songs Y to the change in time X. What is the rate of change? So if we think about the words rate of change, you've heard the word rate before. Rate and ratio kind of go hand in hand. If you've ever heard anybody talking about driving cars, your speed is 60 miles. If you're going 60 miles per hour, you're going 60 miles for 1 hour. That's a rate. If you've been to the grocery store and you've bought produce, apples are 99 cents per pound. That's a rate. So in this case, we have the number of songs per minute. Okay, so that's our rate. So write this down somewhere on your page. So the rate is the number of songs per minute. Okay, let me make that a little more clear for you. Okay, now they're asking us, what is the rate of change? And what that means is if our rate is number of songs per minute, if we can look at the change, then we can get to our rate. So once we know our rate of change, then it's kind of like the pattern. Okay, so our rate of change is trying to figure out our pattern. So compare the change in the number of songs Y to the change in time X. So let's look at our change in the Y. Our change in Y, what's happening from one to the next? So in number 1, right, change in Y, is it increasing, is it decreasing? If it's increasing, how many is it increasing by? Those are the questions you want to ask. So we would say increase by 2 minutes. Oops, excuse me. It's not minutes, Y is songs. Okay, so each increases by 2 songs. Then we're going to look at the change in the X. We look for our X from one to the next. Are they increasing or are they decreasing? They are increasing by 1 minute. Okay, so my rate of change would be increases 2 songs per minute. Okay, so we look at our Y change first, then we look at our X change. So every time we change, we go up by 2 songs in the Y, and we go up by 1 minute in the X. So it increases 2 songs per minute. This right here is your answer to the question. All the other stuff is just extra little notes. Okay, oops. Okay, so then it says graph the ordered pairs from the table on the graph shown. Label the axis, then describe the pattern shown on the graph. Okay, so our X values were minutes. And the Y values were number of songs. Okay, and at 0 minutes we had 0 songs. After 1 minute, how many songs did we have? 2. After 2 minutes we had 4 songs. After 3 minutes we had 6 songs. After 4 minutes we had 8 songs. Okay, so again, if I took the values from that table and I turned them into ordered pairs, these would be the ordered pairs you would have. 3, this was our X, this was our Y. I don't even know if they went up to 4, by the way, but we could assume that 4 minutes would be 8 songs. Okay. So if we look at the pattern here, when you need to describe this, things you can notice, does it look like the number of songs are increasing as the minutes go by? Yeah. So you could write something about the number of songs are increasing as the minutes go by. Is it consistent? If you take a look, is there a pattern? If I were to connect my dots, would it make a straight line and continue a straight line? Yeah, there is a pattern. Okay, now just a little side note about whether you need to connect the dots to make a line or not. The only time you connect the dots is if you're graphing just a straight equation, you will always connect the dots. If you have a real life situation, you need to think about the situation. As I'm going, if you think about your computer as it's downloading something, as the minutes go by, that little status bar increases and increases, right? So at half a minute, I would probably have 1 song done, wouldn't I? Would you assume? If in 1 minute it's 2 songs, after half a minute it would be 1 song. Well, a quarter of a minute, so if I'm only 15 seconds in, I'd probably have half of 1 song done. So you could see that if I gave you any amount of time, there'd probably a certain portion of a song downloaded. It doesn't just download the song instantaneously. It status bars through it, and it downloads megabytes at a time until it gets to the final size of the song. So you could actually connect these dots because there are actual portions of the songs getting downloaded as time goes by. That's just a little side note. But for this answer, you need to do this in your own words. Okay. All right, linear relationship. So here's our first vocabulary word. Relationships that have a straight line graph, like the one on the previous page, are called linear relationships. So your definition is right here. Relationships that have straight line graphs. Okay. Notice that as the number of songs increase by 2, the time in minutes increases by 1. The rate of change, 2/1, 2 songs per minute. The rate of change between any 2 points in a linear relationship is same or constant. A linear relationship has a constant rate of change. So here's your second vocabulary word. Now when you're writing this vocabulary word down, I would write constant rate of change, and then I would write the first sentence down, and then after the first sentence I would rewrite this whole sentence right here. So I would say a constant rate of change is the rate of change between any 2 points in a linear relationship is same or constant. And then I would write afterwards, the linear relationship has a constant rate of change. Okay. All right, so here's your second vocab. Oops. Okay, and if we go back to what is stated right here, just a couple things. We always write the change in the Y over the change in the x. If you see the way they wrote that 2 over 1, this was the change in minutes, the change in songs over the change in minutes. Okay? And you write that as a fraction. It's a ratio. It's a rate. All right, so let's take a look at our first main example. The balance in an account after several transactions is shown. Is the relationship between the balance and the number of transactions linear? If so, find the constant rate of change. If not, explain your reasoning. So a couple things to remember. If it's linear, that means it creates a line. Okay, so when you plot these points or when you look at the rate, is it consistent or constant? If that rate of change is constant, like you have a pattern that you can follow, then it's linear. Okay, so you might want to make a little side note that says, it is linear if there is a pattern. And when I say if there's a pattern, the x's and the y's don't have to have a pattern within each other. The x, from one x to the next you need a pattern, and from one y to the next you need a pattern. So you focus on just the x's and find a pattern. Then you focus on just the y's for a pattern. We don't care if there's a pattern between the x or the y at this point. That's going to help. We're going to find the equation doing that. But to decide if it's a linear relationship, you just focus on the x's, find a pattern. Focus on the y's, find a pattern. Here's what I mean. Take a look at my number of transactions. My number of transactions increase by 3 every single time. Okay? So as my x's increase by 3, my y's decrease by 30. Okay? Now there is a pattern from the 3 to the 170 and from the 6 to the 140. That's happening, but that's not what we're looking at. I just want to say if my numbers for my x's follow a pattern, when they're written, you got to write them in order. If my x's are written in order, if there's a pattern there, and there's a pattern with the y's, then it's a linear relationship. So let's take a look at what we say here. Since the rate of change is constant, this is a linear relationship. The constant rate of change is negative 30 over 3, or $10 per transaction. This means each transaction involved a $10 withdrawal. Okay, so let's break this down. So my rate of change is constant. We know that because of the patterns. Okay, so this means that there's a pattern in the x values and in the y's. Okay, so that's what that first thing means. Constant rate of change. My constant rate of change is negative 30 over 3. And here's what that means. If we look at our y's first. Do you see how my y's are decreasing by 30? Okay. And for the 3, my x's increasing by 3. That's where these numbers come from. The decrease, let me make this a little more clear here. The decrease makes the negative 30. The increase makes a positive 3. Negative 30 divided by 3 is where we get the negative 10 from. Okay? This means each transaction is a $10 withdrawal. So the whole reason that we come up with this constant rate of change is so that we can determine a unit rate. And a unit rate is when we're talking about 1. If I say I drove for 120 minutes or 60 miles an hour, but it took me 2 hours to get somewhere, then I really ended up going 30 miles per hour. If I went 30 miles per hour, then it was 60 miles for 2 hours. So my unit rate would be 30 miles in 1 hour. So if I drove 60 miles, took me 2 hours, that's a rate. My unit rate would be 30 miles in 1 hour. So that's when you get down to the single. So what I have here is 3 transactions, I went down $30. How much would it go down in 1 transaction? We do that by simplifying that fraction. Okay, so what I want you to do now is in that sidebar, you're going to figure out what would the balance be after 5 transactions. And what would the balance be after 15 transactions? You do it however you want to do it. Give me your answer, write down the statement. So make sure you're writing the whole statement down with your answer. And right here, in order to find the balance after 15 transactions, I would blank. So the first one I actually want a number. The second one, I want you to describe to me how would you figure out 15 transactions without making a table. I do not want you making a table. So avoiding the table, okay, because what if I wanted 100 transactions? That's going to take you forever. Come up with a different way. Pause it here and make that happen. All right, let's see if you got it. We're going to do these problems to find out. Okay, so what we want to do here is come up with our constant rate of change for each. Okay, so when we write our rates, the y comes first. Okay, so y is the numerator. X, actually, let me take that back. The y is not the numerator, the change in the y. Okay, so the change in the y is your numerator. Change in x is the denominator. Make sure you write this down. This right here is going to be huge. It's not going to go away. It's something you're going to see repeatedly for the rest of this year, and you will see it repeatedly in high school. Another way you might see it written would be like this. The triangle represents change. Okay, so that's notation for change. Okay, so let's take a look at A. If we look and see how our our y's change in A, let me get a different color here so it's a little bit easier to see. So if we look at our change in the y, let's see what happens. This went down 5. Oh. Then it went down 4. Then it went down 4. Our minutes go down 5. Go down 5. So as we have a constant change for our x's, but do we have a constant change for our y's? We don't. Okay, so if we were to look at, if we were to just take our first section right here, so ignore this part, and if we were to take our first section, my y's change, I say 95 minus 90, so when you find a change of something, you're subtracting, and 5 minus 10. So 95 minus 90 is 5, 5 minus 10 is negative 5. So my constant rate of change would be negative 1 over 1, once I simplified that. However, if we take a look at from 10 minutes to 15 minutes, and we were to find our change in y, so if I said 90 minus 86 over 10 minus 15, see how I get 4 over negative 5? These two numbers are not the same. So that's a problem. So whether you look at it the way I just did it with the subtraction, or you take the pattern the way we did originally, oops, that's a negative 5. Down 4, down 4, up 5. So if I have a pattern on one side and I don't have a pattern over here, then what we would say is not a constant rate of change. Okay, that doesn't mean this is wrong. The temperature could absolutely work this way. You literally could go down 5. It's when the temperature raises and increases, there's no rules. Okay, Mother Nature doesn't have a set of rules to follow. It does whatever it wants. You know, if you're from Las Vegas, it rains one second and then it's blue skies the next. So especially when it comes to temperature, you can't gauge that. All we're taking a look at is to see, is there a constant rate of change? And no, there is not. Not a constant rate of change. And so what that means is since there's not a constant rate of change, that means that this, this is not a linear function. Okay, because it's not a constant rate of change, this cooling water is not a linear function. Okay, copy down anything you need to copy. I'm going to go ahead and erase this page in a second. Okay. All right, so let's take a look at our next one. So if I look here, it's a little bit different when you have a graph. You have a few options. I could make a table from the graph. Let me erase the bottom here. So if I were to make a table from B, I'd have my X's and my Y's. My X is number of volunteers, and my Y is time. So if I take my ordered pairs, when X is 8, Y is 80. When X is 16, Y is 60. And when X is 24, Y is 40. So if we take a look at our change here and see what's happening, my Y change is going down by 20. Down by 20. If we look at my X's are going up by 8. Up by 8. Do you see how both sides have a consistent pattern? Okay. That would mean my rate of change would be negative 20 over 8. The way time changes, 80 minus 60. Or if you want to, you'll see in a second, over 8 minus 16, I get 20 over negative 8. Now, one thing I do want you to notice, if you see how this was a negative 20 up top and over here was a positive, it's just the order. If I wanted to rearrange my order, if I wanted to take the second number minus the first, as long as I take this minus this, I'd have to do 16 minus 8. So as long as I'm going in the same order, I end up with the negative 20 over 8. Honestly, whether it's 20 over negative 8 or negative 20 over 8, it's going to end up being a negative. That's just a little side note. So, for B, because the constant rate of change is, if I simplified that, I would get negative 5 over 1. No, I wouldn't. Let me actually think this through for a second. If I divide each of these by 4, I get negative 5 over 2. There we go. So because the constant rate of change is negative 5 over 2, this is a linear function. So again, if you can come up with a constant rate of change, that means a pattern in the x's and a pattern in the y's, then it is a linear function. Okay, so the next thing that we're going to take a look at are proportional linear relationships. So up until this point, if you had a pattern with the x's and the y's separately, okay, together it's a relation, function or not, that we're looking at whether the x's had a pattern and the y's have a pattern. And if they did, then you had a linear relationship or a linear function. Now we're looking at if it's going to be proportional. Okay, so this is actually something that you should add in your vocabulary page. Okay, so add to vocab. Proportional linear relationship. When two quantities A and B have a proportional linear relationship if they have a constant ratio and a constant rate of change. Okay. If they have a constant ratio and a constant rate of change. Okay. Here's another piece of important information. To determine if two quantities are proportional, compare the ratio B over A for several pairs of points to determine if there's a constant ratio. We're going to take a look at a couple examples. So definitely copy these two pieces of information down. And a little side note, with the B and the A, if you want to change that with the X, make that an X and a Y, or a Y and an X, that's okay too. So every time you see a B, if you want to make that a Y and and the a is an x. That works too. So you could say y over x is constant. Okay. So, but that's up to you. All right, let's take a look at an example. Okay, example number 2. Use the table to determine if there is a proportional linear relationship between a temperature in degrees Fahrenheit and a temperature in degrees Celsius. Explain your reasoning. Okay, so a little reminder off to the side. 2 quantities are proportional if they have a constant ratio. Okay. So, let's take a look at our table. We have degrees Celsius and degrees Fahrenheit. And what you'll notice is my degrees Celsius increased by 5. My degrees Fahrenheit increased by 9. There is a constant rate of change, 9 over 5. Okay, so my Fahrenheit over my Celsius. Since the rate of change is constant, this is a linear relationship. So that's what we just talked about in the last example, is if it has a linear relationship, there will be a constant or consistent pattern. Okay, now to determine if they're proportional, remember proportions are ratios. You looked at proportions and ratios in previous grades. Now we're applying that to these situations. So, next paragraph. To determine if 2 scales are proportional, express the relationship between the degrees for several columns as a ratio. Okay, so here's what we did. I'm going to try to color code this for you. So, 41 over 5. We looked at this piece right here. So now we're directly looking at the x and the y and the relationship that the x and the y's have. Okay, so up to this point, we just compared x's to see if there was a pattern. Then we compared y's to see if there was a pattern. Now what we're going to do is we're going to directly look at the x and the y together as a ratio. So 41 over 5. Next one we're going to look at 10 over 50. And the last one that we looked at was 59 over 5. And to know if it's proportional, each of these ratios, when you simplify them or divide, you should get the same number. And if you notice, did we get the same number? No. Okay, that doesn't mean there's anything wrong. It doesn't mean that the math is wrong. That doesn't mean that this is a bad example. It just means that it is not a proportional linear relationship. So we take a look at the graph. It still creates a straight line. Okay, so nothing strange happens there. All right. If we look at this bottom section, it says graph the points on the coordinate plane, then connect them with a line. The points appear to fall in a straight line, so the relationship is linear. The line connecting the points does not pass through the origin, so the relationship is not proportional. Okay, we're going to back up for just a second. There are 2 major things happening here. This right here is like example number 1. This is the first thing we're going to look at. Is the relationship linear? Now remember, the word linear comes from, well, actually the word line, it comes from linear. So if it creates a straight line, it's a linear relationship, period. The newest part is this proportional. And what you would notice, if you did a few of these examples, you would notice that proportional relationships, the line goes through the origin. Non-proportional relationships, the line does not go through the origin. That is something that you'll find. Okay, so this right here is huge. Okay, what I want you to do, and this is what I'll check this on your notebook check. This right here needs to be added to linear relationship definition. Okay, and this right here needs to be added to proportional definition. This is huge. If you can remember these 2 pieces of information, it's going to be so helpful. Okay, so in the sidebar of the page, I want you to write this statement and then end it with your own words. Although the graph illustrates that the relationship is linear, it's not proportional because blank. We just talked about it. I know you know it. You just wrote it in your vocab, but I want you to write it again on the sidebar. So on the sidebar of this page, write the sentence and finish it. If you're unsure, rewind. Okay, so let's try an example. Use the table to determine if there's a proportional linear relationship between mass of an object in kilograms and the weight of the object in pounds. Explain your reasoning. Okay, so the first thing is we want to see, is it linear? Because if it's not linear, then there's no way it's a proportional linear relationship. So if we look at my x's, it increases by 20 each time. Okay, and then if we look at our mass, it increases by 9 each time. Okay, so there is a linear relationship. Perfect. So now we want to know, so our constant rate of change would be 9 over 20. Right? So we're good there. Proportional. So what we want to look at for proportionals, we want to look at a few of these fractions. So if I say 9 over 20, now when you're trying to decide, you do the x over the y over the x. Honestly, when you're determining if it's proportional, the order doesn't matter other than you need to stick with the same order. So if I did mass over weight, I need to do mass over weight every time. So I would have 18 over 40. And then I would have my third one I'll try would be 27 over 60. So if you take your calculator and you divide, I want you to divide, take each of these fractions and get them down to a decimal and see if we have a proportional relationship or not. So hit pause and get out your calculator and see how you do. Okay, so when I divided, I got 45 hundredths for each. So yes, it is proportional. Because each of these are equal. So you are going to come up in your own way with explaining why these are proportional linear relationships. Okay. Couple notes, common trouble spots, how to determine if a relationship is proportional. First thing, the line must pass through the origin. That's important. If you don't have that written somewhere, like back in your vocabulary, you need to. And the other test is if you put the x and y coordinates into ratios, they will be equivalent. That's what we just did on that last problem, doing 9 over 27, whatever those fractions that turned out to be 0.45. That's the second little spot. So honestly, this right here, especially if you're looking at a table or at a graph, going through the origin is huge. Okay, so a little reminder about a vocabulary, linear relationships, constant rate of change. Make sure you have both of those. And the one I want you to add is proportional linear relationship. So you have 3 words: linear relationships, constant rate of change, and proportional linear relationships. All right, time for guided practice. Now is the point, if you're still a little bit confused, you'll want to go back to the post. There is a video that will kind of give you another example that might help you make sure that the guided practice makes sense. Okay, number 1, the amount of paint Y needed to paint a certain amount of chairs X is shown in the table. Is the relationship linear? If so, find the constant rate of change. If not, explain your reasoning. Okay, so is the relationship linear? So what we're looking for here is we're just looking to see, is there a pattern with the x's, a consistent, constant pattern? And there is. Is there a constant pattern with the y's? Yes, they're each increasing by 6. So yes, this is a linear relationship. Okay, the constant rate of change is going to be my change in y over my change in x. So we're finding the difference in my y's and putting it over the difference in my x's. So if you look at this, my y changed, it increased by 6. My x's changed, they each increased by 5. So 6/5 is my constant rate of change. Constant rate of change. Now again, if you need to simplify that at all, you do. We don't do mixed numbers. Okay, but if this was 12 over 10, we would simplify it to 6 over 5. Number 2, The altitude y of a certain airplane after a certain number of minutes x is shown in the graph. Is the relationship linear? If so, find the constant rate of change. If not, explain why. So if I were to connect my dots, if you notice, if I try to make a straight line, if I put a ruler, let's try this again. If I put a ruler here, I don't actually have a ruler, but if you were to put a ruler, it would not go through that last point. Okay, you take a ruler to your paper or take the edge of your binder, but if you were to actually attempt that, it would not go through this third point. This third point is a problem. Now, if it looks to you like they would connect, that's okay. What you need to do is you would find that rate of change. So if we're looking at our ordered pairs, it's probably 3,500. So when x is 0, y is 3,500. When x is 2, y is 3,000. When x is 6, y is 2,000. Okay. Now if we look, my x's are going down or up by 2. So I'm going to stick a 4 in here and see if I can figure out what's happening. So for my y's, my y is decreasing by 500. So for my 4, let me pick a different color here. So for my 4, if my x's are increasing by 2 and my y's are decreasing by 500, for 4 it should be 2,500. And then my last one, if you take a look at this is pretty interesting. As my x increases by 2, my y decreases by 500. So to my eye, with my little ruler, they did not connect. However, eyes can play tricks on you. Do not always trust eyeballing it. Don't always trust the ruler. Trust the math. Okay, for me, I didn't see that it went through the straight line. It seemed curved to me, but that was my eyes playing a trick. Always go with the math. Okay, put your numbers in a table. Yes, it is a linear relationship, and my constant rate of change is negative 500 over 2, or negative 250 over 1. Okay, trust the math. Last two, determine whether a proportional relationship exists between the two quantities shown in exercise 1. So you're going to go back to exercise 1 and you're going to determine, is there a proportional relationship? Okay, a couple things I want you to think about. If you were to graph that, does the line go through the origin? If it does, it is a proportional relationship. The other thing you can do is take the ratios. Are the ratios equivalent? Okay, so take a look back at example 1 and see if you can figure out if those two things are happening. So hit pause and see if you can figure it out. Okay, something I want you to look at is if the table that was in number 1, if you look for just a second, if our x is increased by 3, our y is decreased by 30. So I want to backtrack for a second. Let's go up above. So what plus 3 equals 3? 0. So if I were to add a line above everything, my x would be 0. So a number up here, when I subtract 30 from it, would get me 170. Well, that's 200. Now if I were to graph this, we'll go by hundreds just for ease. At 0 transactions, I'm at $200. Is that line going to go through the origin? Nope, the origin is right here. So does not pass our first test. So just from our first test of saying, does it go through the origin, we could say, no, this is not a proportional relationship. Okay, if that didn't make sense to you, you didn't want to go that route, okay, it's making you unclear about with the table and all that, we could try something different. I can take a look at my ratios, and I could say 3 over 170, divide those out. When I divide, I get 0.017. So let's take a look at my second one. 6 over 140 is 0.04, because these ratios are not equivalent, this is a big fat no. So you decide what reasoning you want to give. Do you want to give both of these for a reason? Do you want to give one of these for a reason? It's up to you. Finally, building on the essential question, how can you use a table to determine if there is a proportional relationship between two quantities? That's up to you. I can't tell you what to put there. All I can tell you is that you can use a table, and I want you to think about how you would. We did two different ways. I did one way where we looked to see what the origin ordered pair would be, or excuse me, what an ordered pair would be when x was 0 or y was 0. Does it make it the line go through the origin? Or you could look at the ratio. So you decide how you want to put that into words. Finally, there is a self-check link in online. You may go through the self-check if you would like. You want to check yourself before you do the practice. And finally, it is your turn. Take a look online to see what is required for the practice.